Okay, it's recording. So I'll post this recording. I'm Dr. Andy Lovelace. Those of you watching the recording later, for those of you that missed it, apologies that this review is a little earlier. Um, all of this idea of doing review sessions is brand new. I'm not really endorsed by the department to do this. I just am trying to see how much interest there is, and maybe I can convince the department that we could do these regularly. And for me, it's just something fun. I've taught here 20 years. I know these courses really well. I have a lot of resources. And I think, hey, here's a way I can connect with students. I'm not writing your test, so I'm a third party here. But I want to just point you to a few things. Go to your instructor for what is being covered.
Mm,
Sorry, I'm going to mute
I'll
everybody.
get ready to.
I'm going to mute people coming in. All right. So the only other comments is I've made review sheets for 20 years for these courses. I'm trying to add videos to a lot of them. So if you find something particularly useful or find something you might want added, I'm teaching 126 next quarter and in the summer. So I plan to polish up my materials a little bit. So I'm also using all of you as a guinea pig to see what is the most helpful. Okay, and hopefully you get a benefit out of it as well. Also, what I would like to do before we get started here is to look at some of my review materials. So I'm going to get a page ready for us to see, and I'll just pull it up on the fly here. I know you can't see what I'm typing. I'm just a little worried about my loading of things. Let's go. I'm going to share something else. We'll come right back. I have several exams ready, two of my more recent exams, and I can also pull up exams by other instructors. But since a lot of you don't have exams till next week, I wouldn't be surprised if you haven't started studying. It makes sense. You should be working on homework. But maybe I can give you a few bits of help for now and for then. And I find when I was a student, I always tried to study about a week in advance. I would try to do one or two old exams and try to trick myself into thinking the exam was tomorrow. And it really helped me. So let's pretend your exam is tomorrow. Boy, that's a terrible feeling, probably. But let's pretend it's tomorrow, and what you would need to look at. So my 126 material is right here. I think it would be, if you're trying to collect your thoughts about chapter 14, this would be a good place to go. I tried to put it all on one page. I did this years ago. But chapter 14 was about surfaces. You learned how to think about surfaces, meaning a function of two variables, how to find partial derivatives, how to find second partials, how to find tangent planes. Almost always an exam has a question on that. Okay. And then you have several things you did with max and min. You did applied max and min, you did second derivative test, and then the biggest one was this absolute max and min because it has a lot of steps. But really, this is what's going on. Okay, the other thing you're doing is chapter 15. And chapter 15 is there's things you're working on right now, but really every single problem fits the following mold, which is you're given a function you want to integrate or find the volume under. You describe a region, and then you set up the bounds for that region, which allows you to compute. And if you're not including 15.3, then you haven't done the polar piece, this last piece, but you have done the other pieces. So that's what this exam is. It's a lot different than exam one because it's surfaces instead of curves. So a lot of that vector stuff is gone. Usually students are happy about that. Beyond that, I want to share something else. 126. Not that link. I clicked on the wrong link. I'm going to mess up everything again. Okay. This YouTube channel is only about 9 months old. I started doing this last spring. I really started making videos this fall. And again, I'm just trying to pair this with all those review materials. But if it's useful to you, the things to check here would be two places, two playlists. But this one, the 126 exam prep, and then the 126 supplemental videos. Supplemental videos are going to be older, like I made during the pandemic, and you'll have to see my gross hand there, whatever. But this playlist, I did not mean to start that, has a few things I've just created over the last few days. So I'm trying to make topic specific reviews. I'm curious how helpful those are, but I made just an exam two review kind of by topic. And each one just says a little bit about each of those topics. So I did surfaces in general, and then I did critical points, global max and min, double integrals, and then polar. So a lot of you aren't going to need to watch the polar one. Some of them got a little longer than I wanted, but you can fast forward through whatever. But that's a place to go. Okay. I also have like old exam walkthroughs. You can see I went all the way through a couple of my old exams, but I'm trying to start to be more organized. So I'm saying all that because we can only accomplish so much in an hour. If you, I don't know, I don't necessarily suggest you watch all those. I think maybe better is to work through old exams. Then if you find a topic you're struggling with, maybe one of those things will help. Um, all right. So I think that's what I wanted to show you. Now let's flip back. And thank you for those of you coming here. I know you like, I don't have an exam till next week. Um, I had thought of trying to flip it, but I can't find any other times when I can do this over the next several days. So that's what is going on. Um, maybe just to see if you're still alive. Who wants? Does anyone want to see partial derivative practice as part of what we're doing today? Kind of curious. Let's do an initial snapshot of among these topics. I imagine the one you're most worried about is double integrals because you're doing it right now. Which topics might you want to see? Absolute max and min, double integrals, lovely. And sorry, I haven't had a chance to like test my audio. I assume you can hear me, but I'm not. Oh, maybe did it switch to this mic? Let me double check. Like I said, I had everything perfectly set up and had to switch to my where. Okay, this is this mic. Tangent plane stuff. Story problems of setting up equations. Okay, so that's good. I do have a lot of stuff about this. You guys are hitting good topics. So some of you are talking about what I would call applied max and min. And I have some of those. I heard a mention of tangent planes. I really think of tangent plane questions mostly asking you about partial derivatives. And I'll try to make that case. Double integrals. Okay, so there's interest in all the things. Complex optimization. Okay. Double integrals. Thank you. I'm just reading through my pieces. Great. So let's start with a tour. So what do I mean by that? So I have three of my old exams right here that I grabbed. That should say 2023. And some of these I might have done elsewhere in a video, but it's kind of nice to see everything together. Okay. So here we go. This is my spring 2023 exam. If you ever want to see this, you can just go to my 126 page. I don't have it all easily to pull up because I don't have it set up. So we'll just move forward. So let's look at this first question and see where it takes us. So that's a partial derivative question. There's a mention of the word tangent plane. And I don't know that we're going to go all the way through each one of these. I'm just going to kind of make some notes here and then we'll see. So here's a tangent plane. Let's talk about structure here since we're just touring an exam. So think about what your final answer will look like in a question that asks for a tangent plane. So that we can like write what our final answer looks like immediately. So in fact, let's put it down here. So I'm going to leave a little space and I'll try to find if there's ways that I can ask you to blow up the chat here in a second. Okay, so my first question to blow up the chat is I want to put a number, how about right here? What number am I going to put here? That we can do immediately. Two. All right, you're with me. So that's two, that's one, that's one. They gave us those. So the fact that it's a tangent plane question doesn't bother me. What might bother me is I need to do some partial derivatives. I need the partial of z with respect to x. And once I figure that out, it's going to go here. And then I need the partial of z with respect to y. And once I figure that out, it goes here. So this is really a partial derivative question. I feel like this is short enough. Maybe we should just launch into that. We'll do this one because it hits this particular thing. Um, I don't know if I did this one in my practice. I don't think so. So I think this is one you can see more of this in, I think it's part two of my little series of reviews. I've been trying to think of how to break things up. So you could try this one. So we have a rather unusual, well, I don't want to get too sidetracked. Let's just see where we're at. So here's what we have. And back in 14.3, you were doing all sorts of messy partial derivatives. This is a little messy, but let's do a couple little things here. I'm going to write it twice because we're going to do the partial with respect to x, and then we're going to do the partial with respect to y. Which exam is this? This is spring 23. And it's by this really mean professor. His last name is really scary. Loveless. Just sounds like a villain. Wait, that's me. Uh, okay, so here we go. Um, you don't have z by itself. And so when someone asks you for the derivative of z, I mean, when I write this question, I'm testing, and I have a whole part of a segment of my lecture on this topic where I talk about the roles of our variables. And that notation means x is a variable, it's the input. Z is a variable, it's a function of x, and we're thinking of it as the output. And if there's any other symbols in the problem, we treat them as constants. And so this really is an opportunity for us to clean up our understanding of derivatives, among other things. So what I would say is I need to worry about those three things, four things. Okay, and here's how I teach derivatives. Yep, the Zoom will be uploaded later. It's really choppy on my end a little bit, so I hope it comes out all right. Again, I'm using my old computer. This will be the last time this happens, but I just did not realize my new computer didn't have Zoom on it. Okay, so here we go. Here's how I teach derivatives. I tell students to identify how many terms you have. There's four terms there. A term is something completely separated by a plus or minus. This is all stuff you did in Math 124, but this really forces you to show an understanding. The next thing I do, coefficients come along for the ride. There's only one coefficient. Actually, there's two coefficients I see there. There's this 6, and there's this y. It's in a weird spot. We never write what's the derivative of x times 7 because we always put the 7 in front. But the derivative is still 7, even if it's afterwards. So that's what's happening here. So a coefficient is a number that's sitting next to our variable. So there my coefficient came along for the ride. And that's probably overkill for some of you, but since it's our first partial derivative, I wanted to say that. Okay, so now we need to take derivatives. Are there any terms that don't have an x in them? There's one. And so the number one mistake people usually make is they're just moving too quickly through the test and they get this one wrong. So what should I put right here? Just zero, yeah, or really nothing. But and then now we're down to this just taking the derivative of these things. Now the derivative of x is just 1. So I hope this sort of helps. I know this is something people miss on the test, so that's why I took a little time here. The derivative of the other side, we have a function of x trapped inside of a square, and there's a method for doing that. You take the derivative of the outside, it's the chain rule. Then you multiply times the derivative of the inside. We don't like to write it that way though, because we have to keep putting these x's in here. So this becomes 2z to the first times dz dx. Now, when you get to the applied problems, you don't have to do that very often. You don't have to use implicit very much, but this is just testing that particular skill. And I do think some of the other instructors are mean like me and have asked things like this, but I don't think it's that mean, hopefully. Um, this was y. How do I do this term? And I feel like this is a big part of what this question's about. I need a rule because there are two variables there. Neither one is being treated like a constant. I need the product rule. So it's first times derivative of the second plus the derivative of first. Thank you for that. So first times derivative of the second, which is this dz dx, plus the derivative of the first, which is 2x. Ooh, I switched reds. Times z. And so I like these examples simply because a lot of students say, why don't we use the product rule here? Well, because y is a constant. So you don't need to. Okay, so there we go. Questions on that first piece. Again, that probably wasn't the main question people had, but since it was there. Tangents to the trace. I'd have to look at the particular question you're talking about. So maybe we'll come back to that towards the end. Sorry to push it off, but I need to think about what you're talking about. A tangent line to a trace. But anyways, one comment is our goal is to get dz dx. In these problems where I know I just need to do a computation, I usually just plug in my numbers right now. This is just a small time saver, meaning once I'm done taking the derivative, there's no reason to keep your variables if you know you're just computing. So this is 1, this is 1, this is 2, this is 2, this is 1, so we get 12. So this really does save you a lot of time. Equals 4 dz dx plus 4 plus 1. So we get 8 dz dx equals 5. And that means this number is 5/8. Yell at me if I made a mistake there, but I just wanted to get that out. Okay, I think I'll move forward unless there's a strong interest. Now, if you should try this one on your own, then check my solutions and see that you can get that number. So that's partial derivatives, a little bit of tangent planes, and it also has this implicit. So we hit a few things there. Cool. Thumbs up if you want to move on. I don't know if I can see the thumbs up. Or maybe no one's giving me a thumbs up. Oh, I can see it now. I just had it in the wrong spot. I got it now. I can see it. All right. Um, I did this next question in my video. So you might think about this one. I have this one I did in my double integrals intro video. Let's keep touring then. And I'll do one like that at some point. Then we have a find and classify critical points. So think about what you would do there. Take the partial derivative, set them both equal to 0. We can do something like that. We have a reverse the order. A question like this is asking you if you can draw the picture that goes with this region. So if you haven't caught on to that, that's what it's asking. Can you draw that region? That's a fairly quick exercise. Maybe we should do that while we're here. So I am kind of just touring this first exam, hitting a few things as we pass them. And then maybe we'll dig in a little deeper on the next exam we look at. So my question to you is, can you draw the region that goes with these bounds. That's usually a challenge for students. So let's play this game. You do have to remember that these go with the y, those go with the x. Let's make it a little bigger, slightly fuzzy. And so several tips that I always give in my class. One is the outer bounds are the tick marks. That's how I think about these. This is the tick marks. And these are the functions. I'll say why I say that in a second. So what this is really telling me is that for each x value, where x is between 0 and 2, I'm going to give a pattern for where to walk in order to mow the lawn of the region I'm talking about. So what I mean by that is x could be 0, it could be 1, it could be 2, it could be 0.7, it could be... So I'm going to give you an x value somewhere in here. Let's just label a random x value somewhere in the middle here. And I'm going to give you a lawnmower, and I have some region up here that's my lawn, and I want you to walk and turn the lawnmower on when you get to a certain spot. And the spot you're going to get to is y equals x squared. That's the lower bound. That's where we're going to start. So I need y to be between there and below y equals 4. So those are the two things I need to graph. And the y equals 4 needs to be the higher one, and the y equals x squared needs to be the lower one. So that's the important way we think about this. Okay, so I need to draw y equals x squared. Well, that looks like this. Y equals x squared. I don't know why I got tired there at the end and didn't finish it. There we go. So there's that. And then I also need to draw y equals 4. So here's y equals 4. And think about what part I should shade. Should I shade all of this? When should I start shading? Think about that for a second. The other thing I'll notice students will do sometimes is they'll draw a line here. And that adds even more confusion. Do I shade this? Do I shade that? Do I shade this? I don't know what to shade. And that's why I like to say these are just tick marks. Don't draw a line there. They're just telling you where to start and end your pattern. The actual thing that tells you when to turn the lawnmower on is the function. We're mowing from there to there. And we're starting at 0. So all we're doing, I'm kind of taking time here because in my experience, this is a major stumbling block in chapter 15. Maybe it makes perfect sense to you. But we're just trying to walk on every point in this region. We're trying to describe it in a certain way. And the way we're describing it is for any x between 0 and 2, we're going to go up to x squared, which is what this is. And those of you that took Math 125 from me might be remembering, this is why I emphasize this so much. I know it's going to keep appearing for many courses. See, I don't remember that. You did a bad job teaching us. Well, that's probably true. This is 4 here. And that works everywhere. Okay, so that's the main, to me, that's where all my energy goes. You can see I took a bunch of time there. With practice, you can generate that picture very quickly, but that's how you should think of this question. Because the moment I'm done drawing the picture, I feel like I'm done with the problem. And what do I mean by that? So now I have this picture. I have this. And instead of doing it in terms of x, I'm going to do it in terms of y. So I'm going to write a y here, and I'm going to search for a pattern. And once I have a picture, I'm pretty darn good at that. What's the smallest y can be? What's the biggest y can be? Well, I can see it. It's 0 to 4. 0 to 4. And then based off of y, what's the smallest x can be? And what's the biggest x can be? So what is that x coordinate? And what is this x coordinate? That's what the question's asking. It's just asking you to mow the lawn a different way. I think about this every season when baseball season starts because they mow their outfield in so many different ways. Here we mowed it vertically. Now we're going to mow it horizontally. So where do you walk from? What's the lower bound? X equals what? Tell me what goes here.
You did? Was it good?
I mean, it was fine. He was like, yeah, I definitely miss seeing you too.
I gotta move my screen around so I can mute. All right, there we go. So what are you getting for this lower bound right here? What's the smallest this can be? 0, yep. This side, you can think of it as a side if you want, but I think of it more as a point. If I give you a y value, for example, if I said y equals 1 or y equals 2, and then you had to tell me where to walk so that I'm in the region. It doesn't matter where you are, you'd be touching this left side. So it's going to be 0, 0. And when I'm at 3, it's going to be 0. But the upper bound is changing. Can we give a formula for that? Yeah, root, not quite root x, but root y. Because I'm giving you a y value and I'm telling you how far to go. So one comment, if we go back, this is just a general bit of advice. I've drawn on these pictures. This always happens is by the time you get to where you really want to do it, you've drawn all over everything. So let's redraw it here. And this is, to me, this is a 125 skill that's reappearing in 126. And the skill is this. You're either going to label X or you're going to label Y. That's something I personally emphasize a lot. And I don't think the textbooks emphasize it enough. Are we finding a pattern in terms of X and Y? If you're finding a pattern in terms of X, the very next step is to label the pattern in terms of X. So here, this would be X equals 0. Here, this would be X equals, and you get that by rearranging whatever equations you had before. So to me, a 125 student, I want them to have this skill of the moment they see this picture, they see these two pictures, these two ways of describing this region. Now, 125, you were just finding the area. Now we're going a step further with it. Okay, so this should be 0 to the square root of y. And then here we have the inside hasn't changed. Y squared dx dy. And those are the two ways to describe this. The question didn't ask us to evaluate. So several little takeaways. Since some of you are in the midst of this, you're just figuring out this. So several tips for the kind of the beginner to this piece. If this, you can't have your variables escape. And what I mean by that is if this is dx, there cannot be an x here. No x. Because that means it escaped the dx. Okay, if there's a dy here, there can be no y here. Because that would mean it would escape. In the end, you should be getting just a number. This is a volume. There never is going to be variables out here. These are going to be numbers. Okay. So a few little tips. Another tip, if you think you have messed up, pick a random number between these two numbers. Like pick 2 and plug it in here. And if you plug it in and the top number is smaller than the bottom number, something went wrong. So what I'm saying is you can always run a couple little experiments, and I think it's important to understand that if I plug in a 2 for this, it's 0. Okay, 0. If I plug in a 2 for this, it's root 2. Okay, 0 to root 2 at 2. That's what we're doing. Okay. So that's a big part. To me, the biggest part of chapter 15 that's new is you're having to describe regions. Okay, so we spent some time there, but I think there was some important, it's really this labeling. I find a lot of people just, their challenge is they're incorrectly labeling graphs. I have lots of practice for that. So if you go to my materials page, I have a lot of good stuff you can do. I don't get the dx bounds. Good question. So you're talking about this right here? Somebody's asking me a question in the chat. I think they're asking me about these bounds. Yeah, so let's separate. We'll spend just a little more time here, but let's separate the question a little bit. Okay, so first, let's draw the picture even bigger so that I can see everything um, a little better. So I'm going to move my screen around a little bit. Because once we have the idea, this starts to really flow, but there's always this uneasiness for everybody. So let's go back here. I don't think you're asking about the drawing. So let's move past the drawing and let's just sort of break it down into its pieces here. And then this was y equals 2. And this side was x equals 0. And we were trying to describe all the points in that region. So I'd like to give some set of inequalities. So I don't think the question was about any of that. Let me know if I'm wrong there. So now I would like to describe a way to go for a walk and touch every single point in that region. Okay. And we decided we wanted to try to do it in terms of y instead of in terms of x. This is what I mean by if the dx is on the outside, it means you're doing it in terms of x. You're giving someone an x value and then based off of that, computing the y. So now let's do it in terms of y. So you could spend a long time here and say, well, what could y be? Y could be 0, it could be 0.1, it could be 0.2, it could be 1, it could be all the way up to 4. And for every single one of those values, I would like to give an interval. That interval is going to represent how far it is from here to here, and not how far, what the actual coordinates are. And we're going to walk this way. That's why I think of it as mowing the lawn. If you've ever mowed your lawn, you have to go over every blade of grass. Was y 4? No, y was 2. Oh, shoot. You're right. Thank you. Thank you for correcting me. I miscopied. I can only draw a graph so many times before I start making mistakes. Okay, so how would you describe this to someone? You would say for each y value, what can we say? A funny one is here at the bottom. There's only 1 point. You would say x goes from 0 to 0 because it's just this 1 point. At the top, it's kind of interesting. At the top, what are the bounds? If y is 4, what are the bounds? This x value is 0. Yep. 0 comma 4 to 2 comma 4. So it's 0 to 2. That's what we're trying to get is the formula for that. And that's what these bounds represent. Notice the square root of y works because if you do the square root of 4, you get 2. But I'm claiming this is the pattern everywhere, no matter where you stand on y. So I don't know if that's starting to help. So for example, if you were standing at 1, I'm claiming that it's going to be 0, 2, the square root of 1, which is just 1. I'm claiming that when you get to 3, it's going to be 0 to the square root of 3. That's what I'm saying these are. That at 3, it's going to be 0, 3, and then it's going to be square root of 3, 3. And when you're at 1, it's going to be 0, 1, and 1, 1. That's what we're describing. Okay, so if the question is about this, and I think it's after this, I'll move on. The other thing I've noticed is as part of a sticking point for students is just the following. So let's do this little exercise together. So if I label this 3 and I ask you to label this, now it's not to scale. What do you call that? So sorry to break this down. I'm just mentioning a few things here. So what is this length? If this is y equals x squared, and this length is 3, what is that length? It's 9. In general, if someone gives you y equals x squared, I've noticed this is a reason there's sometimes confusion, and this is x, this is x squared. That's what that function means. That's usually not where the confusion is, but I like to start there. Now let's do the part where I've seen lots of errors over the years. If I call this 16 and I ask how far it is this way, I've seen a lot of people label that x squared. And x squared doesn't make sense because I'm giving you 16 for y. So it's not x squared, it's the square root of y. So it's 4. So to me, the number one skill, I really emphasize this a lot in Math 125, is that the moment someone hands me this function, I immediately do the following in my head. If you give me an x, it's going to be x squared. If you give me a y, it's going to be the square root of y. That's what that length was. That's how I immediately knew that this was the square root of y. Okay, that's a bit of overkill. Did I get close to an answer for the person that asked this? It also takes practice. Yeah, great. But it's really important we understand those labelings because if we don't have the labelings, we're not going to be able to do these problems. Okay. So if we keep taking a tour, this one's actually a polar problem. That one's a polar problem. Here's an applied problem. Okay. So I think because I've done lots of those particular problems in my other videos, let me click on just a different exam, fall 2018. Okay, so I think this one, there's several parts of this one I haven't done in other videos. And now I'm going to try to hit bigger topics. This is actually 13.4. So I'm going to skip that, but do check with your instructor if 13.4 is there. Here's a tangent plane. I did do that in my video. We already did a tangent plane question. Here's a volume setup question. There's a polar. There's a reverse the order, but we just played that game. Is this the same global max I did? I find myself always hitting the same questions. Oh man. Sorry to scroll like this. That'd be good to do that, but I'm looking for something here. Okay, let's do this one. There were several people that asked about global max and min. So let's hit a global max and min question. This is, I'm sorry I did all that scrolling. I believe it's fall 2019. I'm sorry, you're going to make you dizzy here. Spring 2019. Think I can help here and demystify this a little bit. I wish I had a 3D visual ready, but I'm not going to be able to get that together in time here. If I was doing this in my class, I would, because it would add a little bit. So what is this question saying? It's saying we have a surface. I always jokingly say to my students, all my surfaces look identical. I draw this picture simply to sort of have something to think about. All my surfaces look like flying carpets. That is not an accurate depiction of that surface, but let's just, for our purposes, say we have this surface. The question asked me for the global maximum. So it's asking me about the highest place I can stand on there. But I'm not allowed to stand everywhere. I can only stand above this region. So if I were to try to draw this in 3D, it's going to look something like this. We're going to have this region. And the moment we do that, it kind of chops off our surface. Our surface now only can go above this. And we're going to erase the rest of the surface. Okay, so now the question is saying, this picture is not accurate at all, but if that's the highest point, then the maximum would be above there. But there's a fundamental idea that you were using in these problems. And the idea was that the global maximum occurs in only one of a few places. And those places are a bump in the inside of the region, or what we'd call a critical point, casually a bump. And we know how to find those. Critical point inside the region, I'll add the words. Or an endpoint. But the big problem you found that was different from Calculus 1, in Calculus 1 and 2, in Math 124, it's nice because there's only two endpoints. In Calculus 3, there's an infinite number of endpoints, and that's what makes things a little worse. There's an endpoint here, there's an endpoint here, there's an endpoint there. All of these are endpoints. And you need to plug all those infinite number of points in and see who wins. Boy, that sounds bad. But the truth is, we just need to analyze them. We don't have to actually plug them all in. So the goal in these questions is to figure out the biggest output. It always ends with z equals something. We'll plug in points and we'll see who wins. So that's the one overarching theme that's true in Math 124 and is true now. If you're trying to find a global max and min, you will plug into your original function and see who wins. We're just trying to reduce the number of things we have to plug in. So this is more of an organizational problem than anything else. And I like organizational problems. So I can give you a plan of attack to handle these quickly. Okay, so let's play the game now. So one thing you need to do is ask, does the surface itself have any bumps? That's how we compute the partial derivatives. So tell me what the partial with maybe tell me what the partial with respect to y is in the chat, because that one I think is easy to type in. Partial with respect to y. Close. What are we missing? Oh yeah, just typed in quickly. 2xy. Partial with respect to x is y squared minus 1. This is the easy part of the problem. This is what's different. So when I solve this, I get y is plus or minus 1. And here's a chance for me to talk about this. There's the first equation. This is not part of this question, but this is how I teach finding critical points. You take one of the equations, you completely solve it as much as you can. In this case, we were able to get all the way to the numbers. If there's more than one case, it leads to two distinct branches. For each one, you substitute that into the other equation. And in this case, when we substitute a -1 in for y here, we get negative 2x is 0, which means x is 0. In this case, when we plug it in, we get 2x is 0, which gives you x is 0. So there's only two critical points. I don't know if it's a bump or not. I don't know if it's a maximum or minimum. It could also be a saddle point. I don't care. All I care is that those are the only places. And I also kind of know where they are. So in a global max and min question, it's like a greedy problem. We're not going to classify anything. We're not going to learn very much. We're just going to figure out which numbers we have to plug into our function and see who wins. So what I just learned is that there are no points inside here. You might say, isn't that inside there? Well, let's see. This is a circle of radius 4. So this would be radius 2. So the 2 points we just found were right here and right here. Those are on the boundary. So honestly, I wouldn't do anything with them. I would just say, well, I'm going to analyze the boundary next. So I'm done there. Sometimes students don't like that. They want to actually have done something. So if you want, you could plug those in. Let's do that. If you plug in -1, 0 and 1, 0, what are the heights? If you were to look up at your function, yes, it should be. Thank you for catching that. Somebody was saying, you put them backwards. So this should be x is 0, y is -1. Oh, well, that's better. It's in the region, isn't it? Oh man, thank you for saying something. Um, X is 0, Y is -1 is down here. This is better information. Good, I'm glad. I just wish I hadn't done it wrong. Whew, all right. So one of those points is not in my region at all. One of them is. So I do need to plug it in. Oh man, what's going on here? So if you plug in a 0, 1 to the original function, so plug in a 0, plug in a 1, plug in a 0, what do you get? 5. You got it. So we have to separate our thinking. This is an organizational piece. That's a really small part of our job. I would say the vast majority of questions you like get no critical points. Whoever writes, when we write a question like this, we have to be conscious on the fact that these questions could take forever if we aren't careful about how we write them. Um, but currently, that's our only candidate. Now we're going to plug in the endpoints. I mean, I find it pretty impressive that we went from an infinite number of points to the inside to only one we had to plug in. But that's the power of what we're doing with partial derivatives and finding critical points. We don't need to plug anything else in. It's kind of like in 2D. If you need to know where something is biggest, you don't look at all these points in between, because that would be silly. You just look at the endpoints and the bumps. That's what we're doing. Okay, so we found there basically is only this one possible bump. So now the structure is very well laid out. We are going to study points on this side and points on that side. So I have two more jobs to do. When I saw this problem, I knew I had three jobs. I had the inside, I had boundary 1, I had boundary 2. So I tell students, if you just write those things, you're going to get most of the points. So as bad as this question might be, the structure is clear from the very beginning. So what do I mean by that? So I need to describe what it means to be a point on this edge. And let's do that. And I would like to plug all of these points into my function and see what gives me the biggest. And then separately, I want to do the other side. And I would like to plug in all those points to my function and see who wins. But I can't plug them all in, so I need to write down what it means to be on this side. So I think that the worry is the same worry we're dealing with in chapter 15, which is how do we describe a region? That's the overarching new challenge in chapter 14 and 15. This was our first time seeing this. You're seeing it in chapter 15. So I would like you to describe what it means to be on this side. That's your goal. So what does it mean for something to be on this edge? We need to categorize that right now. What do they all have in common? Y is 0. And then I tell students, I want you to take it one step further. Not only do you know Y is 0, what do you know about X? It's between -2 and 2. That completely describes that side. So what do you do with that? Now we have something we can plug in. So here's how we have to describe the boundary and then plug in the boundary. What do I mean by that? So if we plug in the point, the Y is going to be 0 if you take a point from this side. And if the Y is 0 and I go back to my original function, I'm going to get X 0 squared minus X plus 5. And we've essentially done it. I'll say what I mean in a second, but I like to, just because these problems are kind of long, I like to tell students, you need to have this clearly presented on your page. I need to see this. And there's one other thing I definitely need to see. So let's go talk about that other thing I need to see. And then we'll talk about how do you do the one variable calculus. But that's a separate thing. Okay, so what about if I have a point on this side? What does it mean to be standing here and looking up at your surface? It means you're on this circle. But is there a nicer way I can write that? It's actually the upper semicircle. So there's a certain way I would like to write it, but I don't want to just immediately do it. So if you're talking about the upper semicircle and you just want to get one of the variables by themselves, which variable would you get by itself? This is sort of a plan of attack problem. I would like to get the y by itself. The reason I want to get the y by itself is because I want all the positive y's. So I'm going to take this equation and get it in a form that is easier to use. And the reason I solved for y is because I knew I wouldn't need the plus and minus. So why don't I need the plus and minus? Because we are not talking about the negative here. So this is what it means to be a point on this side. And similarly, I know -2 is between x is between 2. So what do we do with that? We plug it in. So do watch, if you want a visual of what actually is going on, watch my video on global max and min. I think I have a good visual of that. But what happens when I plug this in now to my function? So I'm replacing y with this. And something sort of nice happens. Whenever I'm explaining these, it always takes a long time. I think with practice, though, you get those three things. So you should ask your instructor, but I tell my students, if I see these three things on the page, you're probably getting most of the points. If I don't see them, you're going to lose a lot of points because I just want to see that you understand how to describe the sides and what it means to analyze the sides. Okay, so that's plugging in the endpoints is just a little more involved. In terms of finishing the problem, each one of those is a one variable calculus problem. One variable calculus problems are the exact same principle, but a little bit nicer. What do I mean by the same principle? You're given an interval, you're given a function. The maximum is either at the endpoints or at the critical numbers. So now is when you get to use your calculus 1 skills. And this is a fairly quick problem. You're always going to plug in the endpoints. Let's do that. So what happens if we plug in a -2? F of -2, 0. So I'm plugging in the endpoint here. That gives me 7, I think, because it's -2 plus 5. What happens if I plug in a 2 here? Now I'm writing all over the place. I get a 3. Now that isn't the end. Are there any other things I need to consider? There's one other thing I need to consider, which is, does this have any critical numbers? This is what bothers students, is they sort of get a routine. They take the derivative, they get -1, they set it equal to 0, and then they give up. When this happens, you should be happy. What does it mean if that's equal to 0? You have -1 equals 0. What's the conclusion about this case? There are no critical numbers on that side, and so we are done with that side. So we should be happy when that happens because there's nothing else to plug in. So this is a one variable calculus problem. You could have also noticed that this is just a line, and a line doesn't have any bumps, so I could have already known this. That's why sometimes people get confused when they're reading instructor solutions, because some instructors just skip that step and don't say anything, and then they're like, what just happened? But it's always going to be either at an endpoint or a critical number, but there were no critical numbers. We're done with that side. A whole lot of work and thought for the fact that now we have 3 candidates. And we effectively have plugged in every point on the inside and every point on that first boundary. And we found out that among those, the biggest you can get is 7 and the smallest you can get is 3. And now we need to finish and do the last points on the other side. So what do we get? We get z. I feel like I want to expand this out. 4x minus 4x squared minus x plus 5. So z is 3x minus 4x squared plus 5. I know a little comment here. This is another one of these things that often gets skipped when you're looking at solutions that instructors write. I know I need to plug in a -2, but it might be interesting for you to look at what happens when you plug in a -2. You get f of -2, and this is 0. Have we already plugged in -2, 0? Yes. And we got 7. Why did that happen? Well, because this endpoint is an endpoint of both sides. And so you really don't need to plug it in twice. Same thing with the 2. If you plug in the 2, you get 3. So I actually don't need to plug that in again. So now we're down to one last thing, if you can keep track of where we're at. We did the critical point inside the region. We studied the first boundary, and we looked at the endpoints, the critical points in there. Now we're studying the second boundary. I plugged in the endpoints. What have I not done? There's a bunch of points I haven't looked at yet. Let's start, maybe I'll start using, what color could I use? So we've considered all of these points. We've plugged all those in. We plugged in those endpoints. We plugged in every point on the inside. What have we not plugged in yet? We haven't considered the points that are actually on the edge. That's a lot of stuff we've forgotten. So what do I need to do? And maybe we'll quickly look. I know I spent extra time here, but we need to find what the derivative of this is and set it equal to 0. That's the critical numbers for that side. We're going to get x is 3/8. And that's the last thing we need to plug in and see who wins. Let me do something here because I feel like this is an important moment. After you do a long problem like that, it's an important moment for us to circle back. Oh, is there a cube there? Thank you. Something did look funny. I'm going to share. I'm afraid to share my whole screen because that'll do this. Okay. Yes, it's x cubed. Dang it. Thank you for paying attention. Okay, so this is 3. This should be 3. And that's going to mess me all up here. Thank you, thank you, thank you. Disheveled today. 3 minus 12x squared. You're going to set that equal to 0. So you don't get 3/8. But let's still do what I was planning to do here. Not my screen. How do I pull this up? Okay, this is what I want to share. So let's pull something up here. And I do want to do some double integrals next, but I think it would be good for us just to briefly look at some old exams. Because the process is kind of long. Ooh, I clicked on my wrong course. I don't know which course I'm in. 112 is what I'm teaching now. They're all mad at me. Okay, so I think we were looking at this exam maybe. Nope. But let's look at this because it's here. Here's a global max and min question. Let's see if you can identify the key moments now that we've done one of these. At the top there, we're finding, let's make a note here. How do I do this? So it's nice. I do this in class, but it's nice after you've done a long one of these. This is the critical points inside the region. And the only point we got was 0, 0. So what we learned is we don't need to plug in anything inside the region. Then we did this boundary, and we just got a constant of 9. That took care of all these points. Then we did this boundary. We plugged in, we got this function, we took the derivative, so we plug this in. Now, back when I wrote this solution several years ago, it was before I was as structured as I am. Now I've learned to put in every little step. It appears I did not clearly plug in the endpoints here, and you'll notice I didn't follow my own advice. I took care of them, I accounted for them, but my solutions are more polished now. And then this last side was this. So I just want to stop and sort of go, can you see where these things came from? I find that if students can do those, the reason there's four things is because there's three sides and the inside. That's fine, Kelly. Yeah. It's equivalent way. So it's good to kind of look at a few of these. Okay. Let's get rid of my annotations here. And do watch my video if these are bugging you, but I think with a little bit of practice we can fill in these pieces. Now, which exam was I looking at? Maybe it was this one. Again, I apologize that not quite as prepared as I'd like to be because my computer didn't work. Okay, this is the one we were doing. Ooh, it's giving me a warning about my audio, but okay, this is it. It looks a little funny because it's a copy. Let's see if I can annotate this again. Annotate. Here we go. So there's inside the region. We did that. We got that there was only one point inside the region. And then we went and did the boundaries. One of the boundaries was this. The other boundary was this, which I chose to solve for y. And somebody is asking in the chat, what if I just wrote y squared? Is that okay? Because I recognize I can just plug that in. That's fine. And then I plug in. When I plug in y equals 0, this is what I get. There are no critical numbers for that one variable function, but I do need to plug in the endpoints. And then I plug this in. This time I did that correctly without those errors. I plugged in those 2 points. I didn't plug in the endpoints because I've already plugged those in. So somebody's asking, good question. They're asking, we already know these endpoints, so why do we have to do this? Is that what you're asking? Yeah. Plugging in those endpoints is only plugging in this point and this point. It isn't plugging in any of these points that are around this edge. In this case, it's actually missing a solution because there is a place when you get the maximum at this point, and there's a place over here where you get the minimum. So how do we analyze those points? Well, we can't assume we're at the ends. So when I say endpoints, I mean anywhere on the edges that you get. I really need my 3D visual. Let's see if I can do, so you have to do that. You have to actually plug it in. That's why I think because that's why I like to emphasize so much that this is what I'm grading. This shows the understanding, the fact that someone gives me those functions. Because that's actually what we're analyzing. Let me say, can I clear all this out? Just too many things to say there. All right, how do I delete, clear all drawings? I'm gonna do one more thing and then let's move past this. So if you watch, let's see here, my global maximum video, I'm gonna turn off so you don't have to hear that guy talk. Okay, so I do a problem on there. So this is a little plug for that. But what I want to show you, which I think is the key that often helps students, is right here. So here's a visual of what's actually happening. So if you're trying to find the biggest point along the edge, you can't just plug in the corners. The corners might be the answers, but in this case, one of the answers is right here on the edge, above this edge. So you need to get those three functions. So if you really want to understand what's going on, watch that video. We basically find the function above that boundary. Then we find the function above the next boundary. Then we find the function, but it turns out the last side has a bump. It has a place right here that we need to find. And if we just plugged in the endpoints, we would only find these two endpoints. We would not find that point. So that's what's happening. Above each side, you get a one variable function, and we need to find the biggest and smallest of that one variable function. But that would be my plug, is to go watch that to clarify your understanding. But let's move past that. I feel like I gave it too much energy, but I'm hoping that you'll all do well on such a question now because you'll have a structure. I'd like to do some sort of double integral. Maybe not that one. We did something like that. Let's just find one. I needed to get more exams. Oh, come on, computer. Give my computer a moment. I think I did that. I feel like I've done all these questions. I know I did that one. I know I did that one. Are there any of these questions I haven't done? uh, oh, we wanted to do an applied max and min. Okay. Does anybody have a particular double integral question or applied max and min from any old exam? I'll try to pull it up. So I'm going to give a moment. And while you do that, I'll pull up my archive. So open questions now, but if it'd be nice for us to do a double integral or an applied max and min, because those were the other things that were mentioned as topics. Sorry, this has gone a little slower than I expected, and we started a little late. Particular question. So some of you have Professor Sue. Let me see if I can pull up her exam and look at one of those. There's an absolute max and min. Oh, you can't see what I'm seeing. A lot of the exams have a little bit of polar, so it's a little harder to find. Let me see if I can grab an older exam of mine. Just letting it load, and I'll grab a question. Would you rather do double integrals next or applied max and min? I feel like we should probably do a double integral. Bear with me here. Applied. Ooh, there's more. Oh, it's a mix. Polar. All right, here's one of these. I'm going to grab something. I know you can't see what I'm looking at. I'm just going to try to do a screenshot here. My computer's very unhappy with me. It'd be hard for it to go any slower. Maybe I can just annotate. Let's do that. If it's refusing, let's see where this goes. Here we go. Okay, coming back. All right. Thanks, Jenna, for being here. If I do one for the final, it will go better. I was thrown for a loop by my unhappy computers. Okay. Just getting a page open. Give it a moment here. It's trying to catch up with me. I know you're looking at a blank page. So here's an applied maximin. This is from my fall 2013 exam. I think you have something kind of like this in your homework. And then we'll pick a double integral after that. So let's read this question, something I haven't done, at least in a recent video. You are designing a box that does not have a top. Oh, there's a one homework question I really don't like because they don't explicitly say in the problem there's no top. I always have to tell students that aquarium problem. Um, well, anyways, hope you got a warning about that. But this is fall 2013. For max and min, I have a certain perspective that I think helps a lot, but you'll be the judge of that. And it's this idea I have of really every question in math. Before we let ourselves be confused, we need to think about what we're given and what we want. That's particularly true in optimization questions where there's so many words that we're kind of overwhelmed and want to run away. And so I always search for the what I want. And I feel like that tells me exactly what to do in the problem. And that's usually in the last sentence. I want to minimize cost. I always feel like the moment I write that down, I know how to do the rest of the problem. I don't know if you'll feel that way, but because of that, I kind of like problems like this because I feel like there's a lot of things I can do. So, what I'm going to do next is do a bunch of stuff to try to find a function for the cost. And I'm going to hope that I can make it a two variable function. And if I can successfully do that, then I will take the partial derivatives, set them equal to 0, and I will be done. So that's why it's so important you identify what you want. In my experience, students that do poorly on these questions don't recognize that they're trying to take the derivative of cost, and they just start taking derivatives of other things. And then it's hard to get much credit. So identify what you want. In optimization terms, we call that the objective. There's no real help in knowing that name. But I always think about it this way. If my goal is to minimize cost, the answer is don't build it. Don't build this thing. Then the cost is 0. So my next question to you is, why do I have to build it? Because they gave me some constraints. There's something in there that says I must build this. So what's the constraint now? This is just a perspective of how we approach all applied optimization questions. The volume has to be 10. Because of that, you have to build it. If they're saying you must make a box and the volume has to be 10, then you have to build it. Okay, so the constraint is the volume is 10. So it is a lot of stuff to keep track of, but if you have this plan, you can separate. So don't ever, ever take the derivative of volume. The only thing you're going to take the derivative of is whatever cost is equal to. We just need to somehow get this information into the cost function so that we can do it. Okay, so that's the plan now. So now we need to do some labeling. You can label however you want. I'm going to call this X. I'm going to call this Y. I'm going to call this Z. And what can I say? Now, there's always this added thing. If you've never bought carpet before or plywood, you might not have encountered this before. So I talk about this. So my students were more prepared for this when I gave this exam. But when you are buying something that's $5 per square foot, when you go up to the cash register, how would they figure out how to charge you? What would your cost be? They would multiply that times what? It starts with an A and ends with a RIA. They'd multiply that times the area of slate you bought. So this is a particular application that came up like in one of your homework questions. I remember students that this is the part they didn't like about this the most, but the answer is going to be, the function is going to be 5 times the area of slate plus 2 times the area of glass. Okay, so that's probably the trickiest part of the whole problem is realizing that. So now let's write that down. 5 times the area of the slate. What is slate here? You notice I haven't even read the rest of the question. I went straight to here. And that's been my guiding light for the whole problem. So I'd just like to pass that on as your approach. What are you optimizing? What can I do to make that a 2-variable function? Okay, the slate is the bottom, and so it's just x times y. I think that is the back made of slate, the front and the bottom. Yes, so the front and the bottom. So xy and xz. So this is slate in the bottom. So we're going to have x times y is the area of the bottom, plus x times z is the area of the front. And then we're going to do 2 times the area of the other sides. So there's this side, and this side. So that's going to be yz times 2, 2yz, plus the back, xz. And this is how this always happens. The moment you've written everything down, you have too many variables. And so now it's good that we have this plan of attack. We want the cost to be a 2-variable function. So anyways, if we simplify, at this point, I feel like I want to expand. So I would write 5xy plus 5xz plus 4yz plus 2. I don't know if there's any of those I can simplify. 5xy plus 7xz plus 4yz. And again, the answer still is I want to make all of these 0, and then my cost is 0. But the only reason I'm thinking that is because I haven't involved my constraint yet. And my constraint is that x times y times z is 10. And so we need to somehow get rid of one of these variables. I'm going to get rid of z. How do we get rid of it? We solve for z. And this is usually the moment when I start to see errors. People start taking partial derivatives because they're antsy to take partial derivatives. They're like, when am I going to be done with this? I need to get on to my next class. So hold off. The only thing you're going to take the derivative of is cost. You plug that in, then we've done it. So once you are there, then you take the partial derivatives, set them both equal to 0, and solve. So I wanted to just talk about the setup because I think that's the worrisome piece. I don't know, does that help at all? If you want practice with that, I do have a video on applied. I do that. The last 2 problems I do in the critical points video. That would be part 2. I do that. And I do have other videos where I go through entire exams, so you can see me do lots more of these. It's only recently have I started to think it would be more helpful if I made them by topic. And I hope to do more of that in the future. But I do have 3 or 4 total walkthrough videos. So I might stop there and do a double integral. But how are we on setup? Was there some value there? Mostly it's this problem-solving approach of what are we optimizing? Like in the homework, you had questions that said, find the point on the cone that's closest to a given point. Was that one of your questions? And you had to realize you were optimizing distance. You had to find a two variable function for distance, take the derivatives. All right. Don't know if that was helpful or not, but let's look. Boy, a lot of my examples are polar. I'm going to grab another one. So we did some partial derivatives. There's reverse the order of, okay, let's grab these ones. Let's do something that I know could be helpful. And then we'll end with that. And if you want to see the full solutions, that's my fall 2023 exam 2. Okay, let's do both these. How about? We'll finish with reverse the order and a volume given a bunch of words. So let's give that a shot. We'll finish with here. You do a problem, a couple of problems. I'll tell you where this is from, if I can find it. This is from spring 2014. So I'm trying to go further back because I realize I've posted solutions on a lot of these. So spring 2014. So let's do that first. So take a moment, if you have a pencil and a paper, and see if I've accomplished anything today. I want to know what that looks like. And then I want to do it in terms of y. It's currently in terms of x. And I want it in terms of y. And then we'll evaluate. Let's do this one all the way through. Think about what this represents. Think about what that represents. Thank you all for being here. It's nice to see several familiar names there. Okay, so let's see how your picture looks. So if it's helpful, this is not a necessary step, but you could say the bounds they're giving me are this. X has to be between 0 and 3, and based off of X, they're telling me Y has to be between 9 and X squared. I would call it a top-bottom region, but the reason I think of it that way is it's currently set up in terms of X, and if it's set up in terms of X, then they're telling you the top and bottom. They're telling you this is the bottom, and this is the top. So I'm just trying to say it a few different ways, because sometimes a certain way resonates with people. That's how it's given to me. And for whatever reason, I want to switch it. Here we want to switch it because actually I don't think there's any good way to integrate it as is. So let's try to switch it. So now I would like to have it all in terms of y. But we need to draw some things. So first off, this is my advice. Think of these as tick marks. So they're telling you it goes from 0 to 3. And then I want you to graph these two things. If you just want one thing to remember, a good first step is to graph the inner equations. meaning graph y equals 9 and y equals x squared. That's a good first step if you're confused. But so you could make a note to yourself, do that first. That's something you have to do. Um, it's better to do that first. Okay, so we need to draw. I'm not going to draw the negative stuff this time because I know it's between 0 and 3. So I'm just going to draw the parabola like this. And I'm going to draw the line y equals 9. That's it. Now I'm going to do a little double check. When I plug in 3, I get 9. Okay, so it goes all the way to there. This is my region. That's really what this question's about. With practice, you can see it. I mean, that's where you sort of want to be eventually. You can see that this goes with this, but there's no expectation that we're there yet. But that's where we sort of would like to be. So I'm giving you steps to be able to see that. Once we can do that faster, then that's how we think through and flip it. People like look online and they find things about special tricks, like if this is a 0 or if one of them's a variable. Those are not going to be general. We can always find a question we could ask that requires you to draw the picture. So you just got to embrace draw the picture. Okay, so now we'd like to everything in terms of y. So once again, a chance to label. If this is y, you could even just label the points. You could be like, if this were y, what is this? If this were y, what is that? That's what we're trying to figure out. In terms of y, where would I start and end my lawnmower? That's a pattern we're trying to find. And if you want, you could do, some examples here, but so let's see what our bounds are. Outer bounds, those are easier. You just walk up. When you hit, sometimes I jokingly say, when I hit the region, tell me to stop. Eh, that's what this is. Then you're in the region, in the region. When you leave the region, tell me to stop. So if you're doing it in terms of y, it's 0 to 9. And then the inner bounds, those are like exactly the same as the question I did earlier. 0 to what goes here? Yeah, root y. You're all doing a good job of figuring out a way to type in an answer that's hard to type in. Oh, there must be a better way to stream and do these. Only thing I can think of is Twitch. I tried to do a live YouTube, but it was delayed. So I don't know a way that students could provide work easier. I'll think about that. Okay, so then we have x e to the y squared. That makes it a little easier to integrate. Now, a few specific things. The variables can't escape, but this could come out here. Why can this come out? Well, because that only has a y in it. It's like a constant. That isn't escaping the y. You don't have to do that. I'm just making a comment. When I look at this, I go, oh, that's why this is better. Because the thing that's messy, I now can take out. You can't take it all the way out, and you can't take. So the rule is the variable can't escape when you're manipulating. So this x can't come out because we're integrating with respect to x. This can't go out here because we're integrating with respect to y. So when you look inside here, you should only see y's and never pass that. So there's a few comments of a few things that can tell you if you've done something very wrong. Okay, now what would it be? The integral from 0 to 9 of e to the y squared. This becomes 1/2 x squared. And those of you that took Math 125 from me, you're all experts at integrating, so you're not worried about this at all, right? Uh, oh, it's always easy to make an integration error. So there we go. So there's that. In fact, I probably made an error. I did. The error I made was miscopy. This is the error I'm prone to. I've learned if I'm taking an exam myself, I have to go back and check the key moments. Like, did I copy correctly? I've learned that about myself. So if I was taking the test, I would have gone back and went, where did I mess up? I did not copy down correctly. My brain's not screwed on right. Now, I would have caught it right here because I know there's something wrong with this integral. Thank you. All right. So what needs to be here? It's not funny. I don't, I wish I wasn't making mistakes, but I've started to think that it's good for me to just own these mistakes and see that yes, everyone makes them, but we can try to build in routines to prevent them. Okay, so right here we have a y. And then that we can do. Why can we do that? What's the next thing that's going to happen? This is the other thing that worries students. When I teach Math 126 in the fall, people freak out because they haven't done integration for like a year, or they did integration in high school. So Math 126 is in some ways the hardest to teach in the fall because you have to kind of reteach the integration. Um, the first exam in Math 126 in the fall is usually doesn't go quite as well. It's hard to jump right in as a freshman to 126, I think. Anyways, let's do this. This becomes 0. This becomes 81. This becomes e to the u. This becomes 1/2 because the y's canceled the u. But we're embarking on integration skills now. E to the u from 0 to 81. So it's 1/4 of e to the 81 minus e to the 0. And what's e to the 0? I have a reason I'm asking that. I've had 4 students this week in my other course. I asked them what e to the 0 was, and they didn't know what it was, which is fine. It wasn't something I realized I needed to review. So that was unfortunate. I did not understand that that's why they were getting confused on the question. Um, okay. So the reversing order was the main piece. Let's see one more thing here. I'm sorry I haven't stopped for questions more. Find the volume of the solid bounded by these. This is a common question in the homework. I think at the end of 15.1 and 15.2, there's some of these, and then in 15.3, there's some again. The 15.3 homework, I have to warn you, has a couple big questions right in the middle of it. So I warn students when I'm teaching it, I'm like, okay, they're big because of two things. You got to do the setup, and then they lead to some sort of trig integral, and it takes some, you're doing like cosine squared, you a half angle. It's just a lot of things come at you, and it's kind of a few problems in a row in the middle of the 15.3 homework. So I just like to warn students about that. It's just too many things coming together and a couple of problems. But what do we do? There's so many equations. And part of the reason there's so many equations is even, I like to give this as an example. If I wanted to describe a cube in 3D, which is a fairly simple shape, how many sides does it have? I suddenly am throwing a random other question. It has 6, right? Those of you that have had dice before. So if you wanted a cube, like if I just wrote, give me the object that's bounded by x equals 0, x equals 2, y equals 0, y equals 3, z equals 0, z equals 5, that's a cube. Well, that's a rectangular box. It's not a cube. But it looks complicated because I had to write 6 equations. So it just happens when you move to 3D, you're going to need more equations to bound something. So don't let the fact that there's so many equations scare us. What you just need is a plan of attack. And I've got that for you. Okay, so the plan of attack is there a Z anywhere in there? Now in math, for all the homework questions in Math 126, we do everything in terms of Z. Does it have to be that way? No. But we save other output variables for when you take Math 224, because that adds an extra question, which is which variable do we want the output variable to be? So if you're always doing things in terms of Z, then that's your integrand. So the very first step is you write the double integral of y squared, and I'll be kind of ridiculous, but I'm going to do this here. Every z you see gives you a double integral. If there happens to be two z's, you're going to be doing the volume between two things. Now, in this case, it's just the ground, so I don't need that. But you had like one homework question where you had like another surface. Okay, so if you just want to be a robot, step one, plop this in here. Done. Okay, so that helps you digest and get you started. That's describing my height. Step two, describe the region on the ground. So students who take my 126 from me know that we immediately plop that in there, and the very next thing we do is we draw X and Y. And the rest of the problem becomes describing the region. And there's sort of a two-step piece to that. So it's three steps total, I guess, if you count. Plug in your Z, draw the region. But the two steps here are there any given X and Y bounds? Meaning, are there any equations up here that don't have Z's in them? Yes, there are. Right here and right here. Draw them. So that's the next step. So you're going to draw y equals 3x. Those are actually surfaces in 3D that go straight up. We would call, I guess you'd call them, well, they're planes. Now that I look at them, but one of them looks like this, y equals 3x. And one of them looks like this, y equals x minus 4. Now that confuses me because that does not give a region, but students are like, but that region, but it didn't mention the axes at all. In fact, I should erase the axes. And that makes it really confusing because you're like, it doesn't even give me a region. I just have this line and this line. So how does this question even make sense? And really, they're not lines. They go up like this. But that still doesn't help me. So this sometimes happens in these problems. So either the person who gave this problem, which was me, made a mistake and did not give enough sides, or there's one other possibility, which is that the surface must hit the ground. If the surface hits the ground, then that might contribute another side. And that's why I like to break this into steps. Does the surface hit the ground? Do the z's intersect? This is very general. It took many years to sort of think about what is the simplest piece here. Do these z's intersect? They do. Where do they intersect? If those z's hit, does the surface, my flying carpet is not accurate because it does hit the ground. It hits the ground when y is 0. Aha, that's the other thing I needed. So the two things they gave me were, I got to change the size of that blue. I keep grabbing it. The two things it gave me are y equals 3x and y equals 4 minus x, but that was confusing because it didn't give me a region. The two z's intersect to give me y equals 0. That was the extra side I needed. And y equals 0, that's the x-axis, all the points. So let's redraw this. So the other side is this y equals 0. And finally, I have a region. Anyways, that helps us out. So if I was going to, maybe I will finish by actually graphing that, but if I was going to visualize this problem, that's what's happening. This thing actually hits the ground. It's this. I could even graph it. I try to make these problems simple enough that someone could graph it if they had to, but if you can follow the process, then you have it. Okay, so at this moment, we're ready to go. Now I have a question. Would you rather use X or Y? And to me, there's a clear choice here. So step one, we found our integral. Step two, we drew the given x and y bounds. Step three, we saw where the z's intersected, which was essential here because it gave us the other side. And now we're going to give the bounds. But my next step is to either say, do I want to do this in terms of x? And to me, there's a big disadvantage to doing it in terms of x. And there's the advantage, the problem is what I just drew. What am I worried about if I use x? There is a problem. The bounds change. So I'd have to split it up. I don't want to do that. So if I don't want to do that, and that would be perfectly fine. It would give us the answer. It just would be two separate problems. I'd have to split it up. So I would rather do y. It's kind of surprising when you look at this one because you go, well, maybe. But if I use y, I'm always between green and red. And the moment I do that, now I want to rearrange these. I want to solve this for x in terms of y. So if this is y, then x is, this is funny when you solve this because you get x is equal to 4 minus y. And this point over here would be y over 3. And now we've labeled everything. The only point I don't have is that. I'm going to guess it. I think it's 1. When do these two things intersect? When you plug in a 1 there, plug in a 1 there, you get 3. So at 1 comma 3. All right, so let's finish it off. What are my bounds? What's the biggest and smallest y can be? And then based off of y, those parentheses aren't needed. I'm just using it for emphasis. What are the bounds for x? Once you've labeled everything, the answer is sitting there, but you have to know where to look. So the answer for these 4 things are sitting in that picture. And that's really, to me, the biggest challenge of chapters 14 and 15 is this piece. So think about if you know what those are. Maybe we'll finish with that. It's all in that picture. Let me erase some things that we don't need. Oops. I do need the sides. I don't need this anymore. I've already filled that in. Everything I need is in that picture. What's the smallest y can be? Well, that's right here. Y equals 0. That goes here. What's the biggest y can be? That's there. So y equals 3. Based off of y, what's the smallest x can be? And what's the biggest x can be? So this is y over 3. And this is 4 minus y. Going back to something I said earlier, if you wanted to check whether your answer is reasonable, take a random number between 0 and you could even just try 0. If you plug in a 0 here, what do you get? So I find this to be a helpful little reasonableness check. So if I plug in y equals 0 to this thing, what are my bounds going to be? Well, that's going to become 0 to 4. Is that reasonable that when I'm standing at y equals 0, that this runs from 0 to 4? Yeah, that's reasonable. So that's what we should be getting is these numbers should be starting and ending of when you're walking in your region, when your lawnmower's on. It's surprising that all we're doing is describing how to walk in a certain region. That's all the challenge. I'm always amazed by that really is the new challenge. Is how do we describe, and this is sort of true in 2D and 3D. Like if I wanted to find the average temperature in this room and I knew the formula for the temperature everywhere, probably the hardest part of the whole thing would be describing the room. That's the 3D version of that. If you want to find the average temperature of your monitor of your computer, the hardest part probably will be describing the monitor of your computer. So that's what we're fighting right here. We're trying to measure something that's happening above a certain region. What if Z was a constant? Thank you. Let's do that. So, I got to be careful that the question would be reasonable. But if you change this to 1, what happens? And I have to be careful here because do I have negatives? You know what? I'm going to do something. Well, no, let's leave it 1. In general, what that means is you now unfortunately have 2 jobs to do. You need to compute the volume between the region and y squared, and you need to compute the volume between the region and 1. Sometimes I tell students if you're unsure which one's bigger, just wait till the end and do the bigger number minus the smaller number. But there is something else that would change. And maybe I'll make so think about what else would change. And then I'm going to see if I can this might kill my computer, but I'm going to see if I can do it while you're thinking about that. I'm going to try to pull something up. Come on, computer. You can do it. This is why I got a new computer. My old computer hates me. It doesn't like me to do more than one thing at a time. Maybe that's good. Stop multitasking. Okay. So what else would change? The other thing that would change is the surfaces would intersect in a different place. And that's what I'm worried about here. So when you go to do the intersection of these 2 things, you're going to get y squared equals 1. And so when I would go to graph it, I wouldn't integrate over the whole region. I would stop at y equals 1, which means this would be a 1. So you'd have to compute this. You would also compute the other one of the same bounds. But let's see if we can generate a picture of this. And we'll end with that because it might be interesting. I'm going to try something here. Ah, it's not going to let me. It's not happy with me. I'm going to try to share my whole screen. I don't know if that means the chat will appear, but you're seeing a huge mess now, probably. Okay, so let's pull this up. And I'm going to make this picture. So the surfaces we had, I'm going to get rid of this. I'm going to add, let's do an explicit surface, y squared. That was one of our surfaces. To make the picture look good, I would need a lot of time. I'm not going to make it look good. Now we're going to do an implicit surface, y equals. If it's not z equals, you have to do this implicit surface thing. Let's make it a different color. And I'll show you it in a second once I have all these up. And then I'm going to add explicit surface. No. Implicit surface. Y equals 4 minus x. Y equals 4 minus x. There's plenty of better ways to make this, generate this picture. But I'm not going to think about that now. And I want this to be a different color. Come on. green. So we're finding the volume between these things. And I need to make it go a little further. Let's make this go to 5. We're finding the volume between these. Now, in order to only show you the region, that's where I have to be really clever with my 3D graphing and just show you only part of the surface. But it's this little piece in between. I don't know if I can see it from below. Oh, I shouldn't see the light. Let's get rid of that hole. This is what where you end up spending all your time on things like this. Okay, 10. 5, 10. So we found the volume between all those things. The reason that when we went to do the volume, the reason we didn't get the whole region on the ground initially was because the surface itself contributed one of the bounding sides. So anyways, so if you say I want to throw in y equals 1, let's do that. So let's throw in y equals 1. 1. Let's make it black, whatever. Yeah, the picture's not helpful either. Oh, it changed my equation. Then it would be between all those. So anyways, it's not coming out very well to see. So that's why you have to take my course so that you can see the pictures that I've spent time on to make it look nice. But the process still works. Let's show, and that's why I built this process. Because I mean, ideally you'd like to visualize, but if you're taking a test, you're not going to be able to make some 3D visual. So anyways, I think I'm going to end there. Sorry for the disorganized presentation a little bit, but hopefully it was worth the price. So I like when things are free. I can keep my expectations low. Um, anyways, but hopefully you can now go look on my videos or you can check here. I do talk through that process I was just saying about how to set up problems. And I do have separate videos where I talk about some of those skills. All right, thanks for coming. Good luck on your test next week. Yeah. I don't know if I'm teaching 207 next year. I think they're going to have me teach Math 120 and then teach 125, 126 again. So I'm stuck in calculus forever. Other people move, but all right. Oh, I don't mean to be, I don't even know why that happened, but thanks everybody. Let's stop sharing. Good luck. Have a good week. Now, if it would just let me exit. Come on. Well, at some point it will allow me to exit.